It's easy to get swept up in all the headlines. AI is changing healthcare so fast, it's almost dizzying.
Right.
New algorithms, predictive models, all this amazing tech promising to uh, revolutionize diagnosis, patient care, everything.
Hmm.
But what if the real foundation for this whole data-driven future isn't the flashy AI? What if it's something, well, more fundamental, something often overlooked?
That's a great point.
What's the real bedrock for a trustworthy, data-driven healthcare system?
And that's exactly what we're diving into today.
Right.
Yeah, our focus is really on this evolving and I'd say absolutely indispensable role of the SQL analyst in healthcare.
Okay.
We're going to explore how their foundational work really impacts everything, from day-to-day operations right up to these advanced AI projects.
Right.
And crucially, how a transparent data ecosystem is just vital. We'll look at the risks, the big risks of these opaque black box systems.
Mm-hmm.
And we'll also touch on how things like feature stores and new skills like Python are reshaping what these analysts do.
So our mission for this deep dive, then, is to give you a shortcut, a way to understand why these often unsung heroes of data, the SQL analysts, are really becoming the analytics engineers of tomorrow.
Exactly.
And, crucially, what that shift means for building trustworthy AI in healthcare. Okay, let's unpack this. So when we think about cutting-edge healthcare, it's usually AI machine learning. That's what grabs the headlines, right?
Typically.
But is that where the real value generation starts? What we've found suggests that in these super complex healthcare data environments, the SQL analyst is, well, the indispensable bedrock.
That's a good way to put it.
They're described as the first and arguably most vital step in the analytics value chain. And apparently, devaluing this role, that introduces systemic risk. That sounds pretty serious.
It is serious. Yeah,
Yeah.
think about the SQL analyst as the architect of an organization's usable data assets. This isn't just, writing a few queries.
Right?
It's this meticulous process, collecting data, cleaning it, organizing it, manipulating it, all to create that single reliable source of truth. Just picture a big academic medical center, maybe like UCLA Health. Data is pouring in from everywhere. Electronic health records, lab systems, patient surveys, financials, even public health reports.
Wow.
Yeah, and groups like their Office of Health Informatics and Analytics, OHIA, they actually list data integration, management, governance as core services. It just highlights how complex this stuff is.
So how on earth do they manage all that information, that volume, that variety? What's their main tool?
Well, their mastery of SQL is absolutely key. And it's not just pulling data, like I said, it's about surgically joining different data sets.
Oh, okay.
So linking a patient's record to their treatments, their meds, their discharge notes. They use SQL to filter things very precisely, maybe by specific diagnostic codes, right?
Mm-hmm.
Or to aggregate data, like counting readmissions for a certain condition.
Mm-hmm.
It's really this careful, painstaking craft that builds that single, reliable view of things.
And it sounds like it's more than just technical minds. It's almost like detective work.
Absolutely. Yeah, and it's often called data wrangling, and it's not simple. It's painstaking, yes, but also fundamental.
Okay.
Imagine correcting a patient's weight that was typed in wrong, or figuring out missing medical details, or finding emerging duplicate patient records
Right. That happened.
all the time. And this is the human validation part that, an automated machine learning pipeline just can't replicate easily.
Mm-hmm.
An analyst might know, for instance, hey, that a specific field in the EHR, it got unreliable after the system upgrade last June. That's crucial context an automated system would totally miss.
Yeah, absolutely.
And that kind of insight prevents the whole garbage in, garbage out problem, especially when you're talking about potentially multi-million-dollar AI systems downstream.
So the output from the SQL analyst, it's not usually the final product someone sees, but more like the essential raw materials. How does that flow onwards?
Exactly. Raw materials is a good way to think of it.
Okay.
So take that clean, aggregated data on, say, hospital readmission rates. That data doesn't just sit there. It might feed into an interactive dashboard, maybe using a tool like Tableau, giving hospital admins real-time insights.
Gotcha.
Or it could be passed over to data scientists. They then might use languages like Python or R to build predictive models on top of it.
Yeah.
The analyst's work is that critical first step, making sure everything that follows is built on solid ground.
So for you listening right now, why does this foundational work actually matter for healthcare overall? What's the impact?
Oh, it's everything, really. This foundational work, it enables concrete things.
Yeah.
Initiatives that actually improve patient care, like spotting which treatments are most effective or tracking disease outbreaks.
Hmm.
It helps hospitals reduce costs by finding operational glitches, bottlenecks in how patients move through the system.
Right.
And it informs public health strategies, like maybe flagging a rise in flu cases so officials can allocate vaccines better.
Mm.
The quality of that final insight, whatever it is wholly dependent on how well that initial data prep was done by the analyst.
Yeah.
It really underpins almost every data-driven improvement. Their skills are broad to advanced: SQL, database design, understanding EHRs, and critically, data quality assurance and supporting those advanced analytics down the line.
Okay, here's where things get really interesting, I think. As vital as these analysts are, healthcare is also adopting these black box systems at a pretty fast pace.
hmm
So, what exactly is a black box system, and why is it such a big problem, especially in medicine?
Right, so a black box system is basically one where the internal workings are hidden. You put data in, you get an answer out, but you can't see how it arrived at that answer.
Okay.
And in healthcare, this shows up in a couple of main ways. First, you've got proprietary vendor software, maybe for billing or reimbursement models, where the logic is locked down as a trade secret.
Right, the vendor doesn't want you to see it.
Exactly.
Oh, yeah.
And second, and this is growing, you have complex AI models, especially things like deep neural networks. Their internal logic can be often unintelligible even to their own developers.
Wow, even to the developers.
Sometimes, yeah. And the problem is in medicine, being able to understand, verify, and explain the rationale behind a decision isn't just nice to have. It's a clinical and ethical necessity. You have to know why.
And this lack of transparency, it seems to create this whole cascade of problems, right? Let's start with eroding clinical trust and accountability.
Right. So clinicians, they're trained to use evidence to understand the why. If an AI gives a recommendation with no explanation, it puts the clinician in a really tough spot.
Mm.
They might fall prey to automation bias, just trusting the machine too much.
Yeah.
And then the big question, if that opaque AI leads to patient harm, who's accountable?
Yeah.
Is it the developer,
Yeah.
the hospital, the doctor who acted on the recommendation? It creates this massive accountability crisis. It really hits at the core of medical liability.
And it directly impacts the patient, too, doesn't it? It feels like a violation of patient autonomy and informed consent.
Exactly. Informed consent is fundamental. A doctor can't properly fulfill that duty if they can't explain why a certain treatment or diagnosis is being recommended by an AI.
Mm-hmm.
The conversation changes from, okay, based on X, Y, and Z, we recommend A, B, or C, to just, well, the computer says this. That really undermines patient-centered care and their ability to make a truly informed decision.
One of the scariest risks, I think, that we saw highlighted is this idea of perpetuating hidden bias and health inequities. That's huge.
It is enormous.
Right.
Because AI models are fundamentally only as fair as the data they are trained on.
Right.
So if that training data reflects historical biases, maybe in access to care, or if it underrepresents certain groups, the model will learn and often amplify those biases.
Mm-hmm.
There's this really compelling example of a commercial algorithm used widely in U.S. hospitals. It turned out it was systematically underestimating the health needs of Black patients.
Wow.
Well, it used healthcare costs as a proxy for health need. But because of systemic barriers, Black patients, even with the same level of illness, often generate lower healthcare costs.
Ah, okay. I see.
So the algorithm basically learned that Black patients were less sick or needed less care, which was completely wrong. And because it was a black box, this really profound racial bias went undetected until external researchers dug into it.
That's deeply concerning. And on top of these ethical issues, there are also practical, operational, and security risks tied to vendor lock-in.
Yes, absolutely. Organizations can become heavily dependent on one vendor's proprietary system.
Mm-hmm.
That often leads to really costly support contracts,
Yeah.
makes debugging problems incredibly difficult, and can even introduce security vulnerabilities because you can't inspect the code yourself. You're kind of stuck.
So at the end of the day, these black box systems really conflict with the basic principles of scientific medicine, right? It's like asking doctors to operate on faith instead of verifiable evidence.
That's a very good summary of the core conflict. And this challenge is exactly why there's such a big push now for solutions like rigorous validation protocols, explainable AI techniques or XAI, and doing bias audits before buying a system.
Right.
And also demanding transparent AI clauses in procurement contracts. The whole goal is to move away from systems where the logic is just completely hidden.
So, okay, given all these risks, what does this mean for building trust and actually making better decisions in healthcare? It sounds like data transparency isn't just nice, it's the strategic antidote here, a strategic imperative.
It absolutely is, yeah. Data transparency essentially means making sure that everyone who needs to, patients, clinicians, administrators, can easily access, use, and understand data and the processes that govern it.
Okay.
And the benefits are pretty clear. It builds trust, obviously, with patients and clinicians. It can strengthen the organization's reputation. It enables better, faster decisions because you remove ambiguity. It helps break down those frustrating data silos. And, of course, it helps ensure compliance with regulations like IPI. It's really about openness, fostering credibility and accountability.
And to actually achieve this transparency, there seem to be some key pillars. The first one sounds familiar, uncompromising data quality. That's the foundation, the non-negotiable bedrock, right?
Precisely. And that brings us right back to the SQL analyst, doesn't it? Their role in cleansing and validating data is paramount.
Yeah.
Because frankly, poor data quality is the #1 reason why models become unreliable and decisions get flawed. You absolutely have to get that right first. The success of any downstream ML application hinges on it.
Okay, pillar number 2, robust data governance and documentation. What does that actually look like in practice?
It means having things like clear data dictionaries and data catalogs. We mentioned UCLA Health using Calibra for shared vocabulary, and their OHIA dataset catalog, so people can even find what data exists.
Gotcha.
It also means having complete data lineage, being able to trace data from its source all the way to a report or a model. And critically, documenting the queries and the logic used for transformations. Things like meticulously commenting your SQL code, storing it in version-controlled repositories like Git. That's absolutely crucial. It's the total antithesis of the black box. You're replacing that opacity with clarity that can be audited.
And then empowering people to actually use this well-documented, high-quality data. So accessible and self-service analytics is the next pillar.
Yes, exactly. Empowering users. Again, looking at UCLA Health's OHIA, they provide tools like Tableau, Slicer Dicer, various dashboards.
Yeah.
The idea is to democratize access to data.
Right.
This helps build data literacy throughout the institution so you're not solely dependent on a small central team for every single question or report.
So if we connect the dots here, it sounds like the black box AI problem is often really just a symptom of a much deeper black box data problem.
That's a fantastic way to put it, yes.
Yeah.
Organizations that try to leapfrog straight to fancy AI without sorting out this foundational data transparency, well, they're likely doomed to struggle, or worse. But conversely, if you have clean, well-documented, accessible data that enables AI that is explainable, auditable, and ultimately trustworthy.
Right.
And this is where leadership roles like the Chief Data Office become so important. They need to be cultural change agents, championing this, sometimes unsexy but absolutely essential work of data governance and quality. It's the bedrock for any sustainable AI strategy.
Okay, this all sounds great conceptually, but practically speaking, how do we bridge that gap between the clean foundational data the analysts prepare and the advanced machine learning models the data scientists need to build? This leads us to a key architectural piece: the feature store.
Right, the feature store.
Yeah.
Think of it as like a central hub or a library specifically for machine learning inputs. It's a centralized machine learning specific data system designed to manage features.
And features are?
Features are those measurable inputs that go into an ML model. Things like a patient's age, their latest A1C level, the number of times they visited the ER in the last year.
Yeah.
A feature store basically does 3 main things. First, transformation. Takes raw data and converts it into these ready-to-use features. Second, storage. It usually has 2 parts: an offline store for large amounts of historical data used for training models, often in systems like Snowflake or BigQuery, and an online store for low latency access needed for real-time predictions, maybe using Redis or Cassandra.
Got it. Offline for training, online for predicting.
Exactly. And the third function is serving, delivering these features consistently, whether it's for training a model offline or making a prediction in real time. You can kind of think of it like a data warehouse, but purpose-built for the unique needs of machine learning.
And how does this structure actually solve some of those critical ML challenges? You mentioned something called training serving skew earlier. That sounded tricky.
It's a huge headache in ML operations, yeah. Training serving skew happens when the way a feature is calculated during model training is different from how it's calculated when the model is live in production. This can cause models that look great in development to suddenly perform poorly in the real world. A feature store tackles this head-on. It defines the feature calculation logic once, and then uses that exact same logic and code to populate both the offline store for training and the online store for serving.
So consistency is guaranteed.
Guaranteed consistency, exactly. It prevents those nasty surprises when a model goes live.
That makes sense. It also sounds like it would really boost reusability and collaboration among data science teams.
Absolutely. Without a feature store, what often happens is different teams end up rebuilding the same features over and over again from scratch. It's hugely inefficient.
Right, reinventing the wheel.
Totally. A feature store acts like a central library of production-ready, validated features. So, a data scientist building a new model, say, for predicting patient readmission risk, doesn't start from raw data. They can just pull well-defined, pre-calculated risk factors directly from the feature store. This speeds up development massively.
And it strengthens governance and lineage, too, through something called a feature registry.
Yes. The feature registry is like the card catalog for the library. It's a metadata catalog that tracks everything about each feature. Its definition, the source data it came from, the version code used to create it, even which models are currently using it.
Wow, okay.
This level of tracking provides complete data lineage, which is absolutely critical for debugging models, understanding the impact of changes, and especially in healthcare, for regulatory audits. Plus, feature stores often have capabilities for built-in data quality checks and monitoring for things like data drift, where the statistical properties of the incoming data change over time, proactively alerting teams if a model's performance might be degrading.
And this creates a really important, maybe even evolved role for the SQL analyst, right? They become more like a feature creator or analytics engineer.
Yeah. Crucially, yes. Their deep SQL skills are absolutely paramount here. They work closely with data scientists to define features, and then they author the robust, performant, and well-documented transformation queries that actually populate the feature store. They become the primary builders and maintainers of these reusable feature assets.
And here's the clincher, tying it back to the earlier problem. A feature store sounds like a really strong architectural defense against the risks of those opaque black box vendor systems.
It absolutely is. It's a way for organizations to essentially regain control and transparency because it decouples the feature generation part from the actual model execution part.
How does that work?
Well, imagine an organization like UCLA Health. They could mandate that any external AI tool they procure must integrate with their internal feature store through a standardized API. So even if the vendor's prediction model itself is proprietary, a black box, the organization retains full control and visibility over the data being fed into that model. They can ensure the features are defined consistently, validated internally, and checked for potential bias before they even reach the vendor's tool.
That really shifts the power dynamic.
It fundamentally shifts the power dynamic back towards the healthcare organization, giving them critical oversight even when using external AI.
Okay, so we've established the SQL analyst is foundational. The feature store is a game changer for consistency, governance, and even managing vendor risk. But what about the people themselves? How do the analysts evolve? You mentioned it's not Python replaces SQL, but more like Python complements SQL.
That's the perfect way to frame it.
Yeah.
SQL is, and likely will remain, the undisputed champion for efficiently querying, filtering, joining, aggregating huge amounts of structured data sitting in relational databases. It's unbeatable for that. Yeah. Python, on the other hand, is this incredibly versatile general-purpose programming language. It really shines precisely where SQL's capabilities start to taper off.
Okay.
So a very common and effective workflow now is use SQL for that initial heavy lifting, pulling and structuring the core data, then load that data into Python, often using a library like pandas, which represents data in a structure called a data frame. From there, you can do much more complex things.
So adding Python to their toolkit really expands what an analyst can do. What kind of new capabilities does it unlock?
Oh, it's a massive leap. First, they can get into more advanced analytics and statistical modeling. Python has libraries like NumPy, SciPy, stats models that let them perform sophisticated statistical tests, build regression models, do time series forecasting, things that are difficult or impossible in standard SQL. Second, much more sophisticated data visualization. While BI tools are great for dashboards, Python libraries like Matplotlib and Seaborn allow for creating highly customized, intricate, even publication quality charts and graphs. And third, and this is huge, automation and scalability. Analysts can use Python to script repetitive tasks like generating complex weekly reports, parsing weirdly formatted files, even pulling data from external web APIs. This frees up their time for more strategic, higher value, creative problem solving.
And sounds like it also helps bridge that gap towards machine learning itself.
Absolutely. Python is without doubt the lingua franca of data science and machine learning today. An analyst who is proficient in Python can actively collaborate with data scientists.
How so?
They can understand the data scientist's code, they can contribute directly to feature engineering efforts, and they can act as this really critical translator between the raw source data, which they know intimately, and the complex models being built. It smooths communication immensely.
For analysts who are currently strong in SQL, is learning Python a difficult leap?
It's generally considered quite accessible. Python has a reputation for its clean, readable, and straightforward syntax. Plus, there's a massive, incredibly supportive online community and tons of free learning resources available. The barrier to entry is relatively low compared to some other languages.
And strategically, for a healthcare organization, investing in upskilling their existing SQL analysts with Python seems like a really smart move. Probably more scalable and cost-effective than trying to solely hire legions of PhD-level data scientists.
Precisely. Your existing analysts already have incredibly valuable assets, deep knowledge of the source databases, irreplaceable institutional memory, domain expertise in healthcare, and strong logical thinking skills for data manipulation.
Right.
Often the missing 20% is just getting comfortable working within the Python ecosystem.
Yeah.
Upskilling them leverages all that existing knowledge.
Mm.
And this effectively creates that new, more powerful role we talked about, the analytics engineer, someone who combines the rigor of SQL with the flexibility and power of Python. This builds a much broader, more versatile, and deeply integrated analytics team. But importantly, this requires organizations to create formal, funded, upskilling pathways to make it happen.
So, putting this all together, what does it mean for leaders at places like, say, UCLA Health? What are the concrete steps they should take to build this kind of trustworthy, future-ready analytics foundation?
Okay, based on everything we've discussed, the first recommendation is really to elevate and evolve the analyst role.
Okay.
This means formally recognizing the shift from SQL analyst to analytics engineer. Broaden their responsibilities to officially include things like data modeling specifically for analytics, doing Python-based tasks, and contributing to feature engineering. And then, crucially, implement a structured, properly funded upskilling program. Focus it on practical Python skills, pandas for data manipulation, maybe some API interaction skills. The justification here is clear. You're leveraging valuable existing talent, which is far more cost-effective than trying to hire everyone externally.
Makes sense. Okay, recommendation 2 sounds like a bigger investment. Invest in a homegrown, governed feature store?
It is a significant investment, yes. This needs to be an executive-sponsored initiative, likely involving leaders like the Chief Data Officer and the Chief Medical Information Officer working together. They need to build the business case and lay out a multi-year roadmap.
Right.
Position it clearly as a core investment in foundational data infrastructure. The goal is for this feature store to become the single source of truth for all future machine learning development. Why? Because architecturally it's the most robust strategy we have right now for mitigating those risks associated with black box AI.
Okay, third recommendation. Institute a rigorous, transparent AI governance policy. This sounds like it involves policies and contracts.
Exactly. Develop and, more importantly, enforce a new procurement policy, specifically for any vendor-supplied AI or ML tools.
What should be in it?
It absolutely must contractually mandate specific levels of transparency. This could include forcing vendors to conduct and share results of internal bias audits, demanding clear documentation of the model's limitations and the demographics of its training data. And where technically feasible, requiring vendor models to integrate with the organization's internal feature store via APIs. This gives the organization that data oversight we discussed.
Right.
And alongside the procurement piece, establish a permanent interdisciplinary AI ethics review board. Get clinicians, analysts, data scientists, legal folks, maybe even patient advocates in the room to review any high-risk AI applications before they're deployed. This directly tackles those significant legal, ethical, and clinical risks head-on.
Okay, and finally, recommendation 4. Champion a culture of data transparency and documentation. This sounds like it's about the people and the environment.
It is. This involves embedding these values into the day-to-day. For instance, revising performance management criteria for analytics staff. Maybe tie career progression partly to the quality of their documentation, the reusability of their code, and their contributions to shared data assets like data catalogs or feature stores. And critically, executive leadership needs to be banging this drum constantly, consistently, publicly communicate why this foundational work matters, celebrate the wins, successes in improving data quality, better governance, good documentation. That's how you embed transparency culturally and make it stick for the long term. So bringing it all together. Look, the future of healthcare is, without a doubt, going to be shaped by data and AI. That's clear. But the organizations that truly succeed won't just be the ones that buy the fanciest, newest technologies.
Right.
They'll be the ones that build a really resilient, transparent, and trustworthy foundation upon which they can safely and effectively deploy those technologies.
And that foundation, as we've really unpacked today, it's built by people. It's built by these SQL analysts evolving into analytics engineers, working within transparent systems, using tools like feature stores. This foundational work is what allows us to harness AI's incredible power safely, ethically, and effectively.
Exactly. And maybe a final thought to leave folks with. In this vision, the SQL analyst isn't some kind of relic from an older era of just running reports. They are, in fact, the critical, absolutely indispensable enablers of a more intelligent, a more transparent, and hopefully a more equitable future in healthcare.
That's a powerful way to frame it. Thank you for joining us on this deep dive. We really encourage you to think about how these principles, transparency, foundational data work, evolving roles, might apply in your own field, even if it's outside of healthcare.